Now that we have that little bit of that little aside out of the way, let's go ahead and start analyzing some antenna types. And we're going to begin with what's called the infinitesimal dipole. It's a dipole element of a very short length L. This is also called the Hertzian dipole, or just an electrically short dipole. And the reason this is done is that the derivations of all antennas after the Hertzian dipole are largely done by summing a large amounts of short antenna elements. So larger antennas will often be analyzed by just summing antenna as if they were a bunch of these just stacked one on top of one another. And what we're going to do is we're going to apply a current to a very, very short linear wire element, and that current is going to be a sinusoidal current so that it radiates. I0 cosine of omega t plus alpha, which in its phasor form is just, we say that the phasor current is equal to I0 e to the j alpha. And the value in the Hertzian dipole is that we know that this piece of wire is actually a transmission line, and the value of current along the transmission line is going to be dependent on both time and distance along the T line. Well, in the Hertzian dipole element, we're going to approximate that it's only dependent on time. We're going to say that it's independent of distance. So we're going to say that current along this antenna is constantly valued due to the fact that this length L is so short. And for that assumption, it can be shown, I'm not going to prove it, but it can be shown that the magnetic field, electric field, and power density measured at a point O away from the center of the Hertzian dipole, the magnetic field at point O, the phasor form of it, is equal to J times IS times the length of the antenna element times beta, which is just given by that omega, or the relationship with that omega term and the material that the wave is traveling in. We divide that by 4 pi. We multiply that e to the minus j beta r, where r is the distance from the center of the radiating element to the point in space where we're measuring the electric field strength. We divide all that by r. Then we multiply that by sine theta, and this is in the a hat phi direction. The equation for electric field strength in its phasor form at a position O in space is very similar. It's J times a to 0 IS times L times beta divided by 4 pi e to the minus j beta r over r sine of theta a hat. And this time it's theta. The power is just the cross product between these two, and I'm not going to do the math. I'm just going to present the results to you. If I were to take the cross product of those, I would get N0 beta squared, I0 squared, L squared over 32 pi squared, R squared, sine squared theta, and this would be in the radial spherically direction. And from these equations, we see that the Hertzian dipole has a E field and an H in phase, and that are orthogonal to one another. And they are also independent in rotation in phi. They only depend on, the magnetic field only depends on your rotation in theta. And so since phi is independent, the radiation pattern for the Hertzian dipole, there's only one major radiation pattern here, and that's for the theta plane. And what we would see is that the 3D shape would be formed, the 3D radiation pattern would be formed if we just rotate this thing around the center axis Z, and it would form us a toroid or some sort of donut shape. So looking at the power equation, we can see that the maximum value of power is going to occur when this function here is equal to 1, which occurs when theta is equal to 90 degrees, which we can see from the antenna pattern plotted here. So P max for the Hertzian dipole is just when the radiation density function is evaluated at R and theta equals 90 degrees, and I think it's pretty obvious that it just is this multiplying term right here. So that gives us maximum power. And this tells us that max power rated by the dipole increases proportionally to beta squared, I0 squared, and L squared, and it decreases proportionally by 1 over R squared the further we get away from the antenna, the weaker the signal. So the higher the beta, the stronger the max power. The higher the driving current amplitude, the higher the max power. The longer the antenna, the higher the max power. What decreases power is how far away we get from the antenna. Total radiated power from the antenna can be found using pattern solid angle. And total power radiated by the antenna, we showed before that formula is R squared times P max times the pattern solid angle. So to solve this for the Hertzian dipole, we first have to just figure out what the pattern solid angle is. And pattern solid angle is going to be given from the integral from 0 to 2 pi, integral from 0 to pi of the normalized power. And then we take that and we integrate across a solid angle. And we haven't calculated normalized power for the Hertzian dipole. Normalized power is just equal to the radiation density divided by the maximum value of it. So it's this function here divided by this function here. You can see that would just leave a sine squared term there. So pattern solid angle is given as the integral from 0 to 2 pi, integral from 0 to pi. For this case, it's going to be sine squared theta. And then d omega is sine of omega, or sorry, sine of theta, d theta, d phi. So this whole integral just becomes the double integral of sine cubed. And if you were to solve that, you would get a value of 8 pi over 3. So now I can calculate P rad. That's going to be R squared times the max value, eta 0, beta squared, I0 squared, L squared, over 32 pi squared, R squared, and then I need to multiply by 8 pi over 3. I'm also going to make the substitution here that beta is equal to 2 pi over lambda. And this gives us the most commonly used formula for totally radiated power of the Hertzian dipole, which is just 40 pi squared times L over lambda squared times the driving current squared. Pattern solid angle can also be used to determine the maximum directivity for the Hertzian dipole. And that's d max is just equal to 4 pi over pattern solid angle. So we get 4 pi divided by 8 pi over 3. And that gives us 1.5. And radiation, we haven't talked about this concept yet, but we're going to now talk about the radiation resistance of an antenna. It is the resistance that represents the power radiated by the antenna. We will find it from the fact that P rad is equal to whatever the amplitude of the driving current is in RMS squared times radiation resistance. And this is just this is power radiated by a resistor. It's just I squared R. So this just says that P rad is equal to I0 over 2 times the radiation resistance of the antenna. And the radiation of the resistance for Hertzian dipole is therefore equal to, we just equate P rad to this half, to the right-hand side of this equation to the right-hand side of this equation. So we get 40 pi squared L over lambda squared I0 squared is equal to I0, oh, I left a squared off there, I0 squared over 2 times R rad. And that allows us to solve for R rad is equal to 80 pi squared times L over lambda squared And so you can see that the radiation resistance of a Hertzian dipole is dependent on length and on lambda, and therefore frequency of the driving current source.